I'd like to get started. We're going to have a little brief ceremony to start the talk because, as I think you probably know, concerning the Mary Ellen Rudin Prize. We hope it's an ongoing, long-running prize. The idea for the prize originated from the Spring Topology Conference. The prize is jointly sponsored by Topology and its application journal, the Spring Topology Conference, and the Summer Topology Conference. And if the winner happens to be fairly set theoretic, the European Set Theoretic Society also is happy to invite the speaker for a talk. So this year's winner is Balázs Strenner, and so I'll try to say something about why he was chosen besides his brilliant work. Balázs is recognized for his exceptional work on pseudo-Anosov homeomorphisms, an important topic at the juncture of low-dimensional topology and dynamics, initiated by Thurston 40 years ago. Maybe I got too much to say here. So in a 75-page paper described as a tour de force of both ideas and technique, he constructed examples of what I just skipped telling you what they were, proving that for a surface with genus G, all even degrees between 2 and 6G minus 6 can occur, and all odd degrees between 3 and 3G minus 3 can occur. The argument is elaborate, deep, and highly original, and some key ideas are ingenious, so wrote a couple of his references. He also solved another 35-year-old problem in this area by proving that there are I probably saying it wrong, Anosov homeomorphisms of surfaces that do not arise from Penner's very general Thurston-style construction. So that was why the selection committee chose this excellent winner. The selection committee, I'm on it, Gary Gruenhaig's on it, Lex Overstegen is on it, Sasha Dernishnikov is on it, and the whole prize is supervised by Jan van Mil, and we have a wonderful advisory board of Shala, Tarunchik, Istvan Juhas, and I might be forgetting somebody, and one of the group passed away, unfortunately. Okay, so I'm joined here with our first winner of the Mary Ellen Rudin Prize, Logan Holm, and Hank Brown is also an editor, as I am, of Topology and its application, so I just invited them to join me to make it a little more ceremonial. So let's introduce Balázs, and Hank, you were going to do the honors of... Come forward. So the prize is $15,000. It's a terrific prize. The winner is expected to participate in the Spring Topology Conference and if possible the Summer Topology Conference, and that's some of the $5,000. And then there's $10,000, $5,000 as a honorarium, and $5,000 to support a research visit to the institution of the winner's choice. So I hope you, in the coming year, think of excellent applicants. They have to be no more than 3 years past their PhD, and let's keep this wonderful award going. So please, Hank.
Just a few words, just congratulations.
Congratulations. Yes, so
here's something that you should show the message camera.
Okay, so can you please join me in congratulations. That's it for the introduction of the Mary Ellen Rudin Prize, and now I turn over to Thomas for the introduction.
So we're very pleased to have Balázs Strenner from Georgia Tech, who will be telling us about number theoretic aspects of mapping clusters.
Thank you, Thomas, and thank you very much for the kind introduction. Right, so I'm going to talk about eventually number theoretic aspects of mapping clusters, but I'm going to start with some other topological problems that first might seem unrelated, but we will come back to them. So the first topic is self-similar tilings. So here's one example of self-similar tiling. This is self-similar because if you multiply the tiling by a factor of 2, then you get this tiling with bigger tiles, and then each of these these bigger tiles can be subdivided in exactly the same way into smaller tiles. So we get back the original tiling. But not only 2, but 2i, negative 2i, negative 2, they are also self-similarity stretch factors. If you think of the plane as a complex number, then multiplying by 2i, that gives us the same new tiling. And also clearly 3, negative 3, 3i, negative 3i, they are also self-similarity stretch factors of this tiling. So looking at another example, so here also 2 is a self-similarity self-similarity factor. So in this case, basically there are 2 types of tiles. There is up to translation. There's the triangle which has the base on the bottom, and the triangle that has the horizontal side on top. And it's true that, again, it's true that after scaling, each of the 2 types of triangles can be subdivided in exactly the same way, in translation invariant way, to get back the original tiling. So, but again, there are also many other numbers, all integer numbers of the 3rd and 6th roots of unity. They are also self-similarity factors of this tiling. So these tilings are pretty boring. So you can ask whether there are more interesting self-similarity factors. And so here is an example due to Richard Kenyon, where there are three types of tiles, and so I colored them using 3 colors. And so it turns out that we can take this colored region and just rotate it a little bit and magnify it by some factor, and then just put that colored region onto exactly the same picture, in a way that every scaled tile is the union of a couple of finitely many original tiles again in the same way. So like every big blue tile is the union of 2 original blue tiles, and the green tile, and so on. So this would be an example for a more complicated self-similar tiling, and this stretch factor turns out to be this number, and this is the root of this degree 3 polynomial. So Thurston showed in the 80s that this number, this expansion factor of a self-similar tiling is always a complex Perron number. So what is a complex Perron number? It's an algebraic integer which is strictly larger in modulus than all its Galois conjugates, so all other roots of its minimal polynomial, except possibly, or except its complex conjugate. So for this degree 3 polynomial, these are the 3 roots of the polynomial. So that's lambda, this is lambda conjugate, and they are larger in absolute value than the 3rd Galois conjugate. So this is a complex Perron number. And just a reminder that an algebraic integer is a root of a monic polynomial with integer coefficients. All right, so Kenyon proved this amazing theorem, proved the converse, that for each complex Perron number, you can construct a self-similar tiling. And the theorem is beautiful, and the proof is also quite beautiful. Yeah, so here is the idea. So first try triangulating. Try creating a tiling with triangles. It won't work. But but if it sort of roughly works, then one can refine the boundaries, iteratively change the shapes, and by a limiting process, one gets a tiling which exactly works. And so, for a bit more detail on step one, so how to get a triangulation which roughly works. And this is the key idea here, that one takes this ring of integers in this number field, which is the extension of Q with lambda, and then so this ring of integers can be embedded naturally into Rd, where d is the degree of the number, as a lattice. And so we have this lattice embedding of z lambda in Rd, and then one can try to create a triangulation of this lattice where so the vertices of the triangles are lattice points, and one would like to do it in a way that so there is this two-dimensional subspace spanned by lambda, so the eigenvectors corresponding to or two-dimensional subspace spanned by lambda and 1 over lambda, and one would like to sort of approximate this two-dimensional subspace using the triangulation. And if one can do that, so this can be made work. I'll come back to this idea and the end. So the second topic is entropies of self-maps of the interval. So here's an example for self-map, continuous self-map of the interval. Here's the graph of the function. And then, so one can define the number of turning points of the function by, well, in this case, there's one turning point, so it's like a local max or local min. In this case, there's one turning point up there, so CF is 1. And the entropy of this function, this is not the definition, this is a theorem of Miserevich and Slank, that the entropy can be computed in terms of these turning points. So the entropy is basically log of the growth rate of the turning points. So, so in this case, so we need to iterate the function. So this is the function f. This is the function f squared, right? So like this first linear part maps onto 0, 1, and then 0, 1 maps onto this tenth, right? So every linear piece gets replaced by a tenth. And so after every iteration, every linear piece gets replaced by a tenth. So next we have 4 tenths, so we have 7 turning points, and so on and so on. So in general, we will have 2 to the n minus 1 turning points. So if you plug it into the formula, we get log 2. So the entropy of this interval map is log 2. Okay, so now what about log 3? Well, you can do the same thing with 3 linear pieces, right? So you have 3 linear pieces. Again, after every iteration, each linear piece gets replaced by 3 linear pieces. So, so from 3 you get 9, and so on. Growth rate is 3, so the entropy will be log 3. So we can ask what values can X, H take. So far it was 2 and 3. Are there any examples? And so it turns out that we can do the same example for any k, at least 1. We can just do this example with slope plus or minus k's. If k is not a nice number, then in the end we like this endpoint is not going to be at 1 or 0, but it doesn't matter. We can always construct this function, and it turns out that this this has exactly entropy, or the exp of the exponential of the entropy is always k. So so this might not be a very good news. So this is telling us that any real number, at least one, arises as exp of the entropy. So maybe it's not a very interesting question. But so Thurston's idea was, let's instead look at post-critically finite interval maps. So let's restrict the interval maps we're looking at. So what does it mean that the map is post-critically finite? So in this case, critical points, we mean the turning points. So we have one critical point, 1/2. That's our turning point. So 1/2 maps to 1, and then 1 maps to 0, and then 0 maps to 0. So this post-critical orbit is finite. And then for this other example, there are 2 critical points, 1/3 and 2/3. Now 1/3 goes to 1, and then 1 goes to 1, and keeps staying in 1. And then 2/3 goes to 0, and 0 goes to 0. So again, we have a post-critical, finite post-critical orbit. And so Thurston showed that this example that we've seen earlier is post-critically finite if the slope is a Piso number. So what is a Piso number? It's a real algebraic integer, lambda at least 1, whose Galois conjugates are all in the open unit disk. So it's an algebraic integer, so in particular there are only countably many of these. So it's a pretty small subset of the real number. So now the question is, can we, are Piso numbers exactly the numbers that arise or not? So what values can xh take if h is post-critical finite? So Piso, we can get Piso. Can we get anything else? And it turns out, yes, there are other constructions that give us something else. But Thurston exactly characterized what these numbers are. And he proved that a positive real number h is the topological entropy of a post-critically finite self-map of the unit interval, if and only if xh is a weak Perron number. So what is a weak Perron number? So Perron number, we've seen complex Perron number before. A Perron number is a real algebraic integer, such that all the Galois conjugates are strictly larger, well, strictly smaller. So lambda is strictly larger than all other Galois conjugates. And weak Perron number allows the other Galois conjugates to have the same modulus as lambda. So a weak Perron number, that's the biggest pool, and then Perron number and more special, and Piso number are even more special. Right, Piso numbers were the ones where the Galois conjugates are inside the unit disk, so in particular they have smaller modulus than lambda. Alright, so the third topic is entropies of free group automorphisms. So let's take a free group, for example, the free group on 2 generators, A and B. And then we can look at the free group automorphism, for example, F which sends A to B and then B to A, B inverse. So capital B denotes B inverse. And then we can see, again, if you keep iterating, what happens with the word. So we start from A, it goes to B, and then B goes to A, B inverse, and then A, B inverse goes to B, B, A inverse, and so on and so on. So in this case, so we get longer and longer word, and we can define the entropy of F just like we defined before. It's the log of the growth rate of the length of the word. So in this case, if you notice, the lengths are 1, 1, 2, 3, 5, 8, and so on. So they are the Fibonacci numbers. So the growth rate is the golden ratio. And so in this case, the entropy will be log of 1 plus square root of 5 over 2, so the log of the golden ratio. All right, so once again, the expo of this number is some nice number, and again we can ask what are the numbers that appear as x page. And so free group automorphisms can be studied by certain graph maps called chain check maps. Here is an example of a chain check map. This example is also due to Thurston. So this picture shows a graph with 2 vertices. So this big yellow blob is one vertex, and this other yellow blob is another vertex. And then we have 7 edges between them. So the fundamental group is F6, the free group generated by 6 elements. And so there's a graph map defined by what's written on the edges. So each vertex is fixed, but each edge, for example, the top edge A maps to A, G inverse A. So that maps to A, and then G inverse and A. And so the train track structure on this graph is the set of legal turns at the vertices. So if two edges are connected inside vertex, then that's a legal turn. If they are not, that's an illegal turn. And so what we want from a chain check map is that basically legal turns go to legal turns. So every edge, every iterate of every edge is a legal path. So for example, A goes to AG, so A goes to A, and then G inverse, so that's legal term, so it's good. And then it goes back to A, so that's also a legal term, so it's good. So now why does this graph map correspond to an automorphism of F6? Well, it needs some work to you need to work a little bit to show that it's an automorphism, so it's invertible, but there's clearly a homomorphism because the fundamental group is F6, so the graph map induces a homomorphism on F6. And so in this case, right, so this problem is, maybe it's not obvious at the first look, but it's very, very similar to the previous problem. And the reason why it's similar is, so what we're looking at here is looking at an element of F6, which is a loop here, and we're iterating that element and see how much it grows, right? So we're taking the loop and iterating the loop and see how long the loop gets, what's the growth rate of the loop. And so the length of the group is just the number of turning points, right? So it's it's very similar to the previous question. And in this case, it's not hard to see it's not hard to see that the entropy is log 3, just because every element is replaced by, or every letter is replaced by 3 letters, and there's no cancellation. So the growth rate of any word is 3. So now Thurston also showed that a positive real number H is the topological entropy of an ergodic chain check representative of an outer automorphism of a free group, if and only if the expansion constant xh is a weak Perron number. There are some words I'm not going to explain in the theorem, but essentially this is saying that isotropies of free automorphisms are also the weak parallel numbers.
It seems a little late.
Say it again?
The date seems a little late.
The date?
Yeah.
Yeah, that's one of his last papers. That wasn't published. I think that's when it was posted on the archive.
Okay.
Yeah. But as usual with Thurston, often his things get published a lot later than he actually figured them out. So the next topic I want to talk about is stretch factors of torus homomorphisms. So now we're getting into more surface stuff and mapping class groups. So let's take a homeomorphism of the torus, and we want to see if what do we might mean by a stretch factor of this homeomorphism. So if you have a homeomorphism, then from the torus to itself, then we can lift the torus to the universal cover, and we can also lift the homeomorphism to the homomorphism of the plane. And after an isotropy downstairs, and choosing the lift appropriately, we can assume that the origin upstairs is mapped into the origin. And then automatically it follows that as a set, the integral points map to the integral points, because Z squared, that's the depth transformation, that group. And then after some further isotropy, we can actually assume that this map upstairs is linear. And since it maps Z2 to Z2, it's in SL2Z. Well, it's in SL2Z, assuming that this was an orientation preserving homomorphism. So in that case, the determinant is 1, and it's in SL2Z. But the point is, most matrices in SL2Z have this description where they have two eigenvalues, lambda and 1 over lambda, where lambda is greater than 1 and 1 over lambda is smaller than 1. And so upstairs we have this behavior that the plane is stretched by a factor lambda in one direction and compressed by a factor lambda in the other direction. And so this means that downstairs on the torus we also have a similar behavior. The torus is stretched in one direction, so there's like a foliation in one direction, and the torus is stretched in that direction and compressed in the other direction. And so, like if you look at the small parallelogram here, it's getting longer in one direction and thinner in the transverse direction. So these such maps are called also homomorphisms of the torus. And you can ask, what numbers appear as stretch factors? So, well, if you just ask this question on the plane, on R2, right, then again, it's not an interesting question because every number, at least 1, is a stretch factor. There's no constraint on how much you can stretch in one direction and compress in the other direction. But for the torus, it's a different question, right? Because as you've seen, this map upstairs is an SL2Z, which means that the eigenvalue is the root of this degree 2 characteristic polynomial with integer coefficients. So this lambda squared minus k lambda plus 1 equals 0, where k is at least 3 if you want lambda to be greater than 1 and positive. so we can precisely describe what the stretch vectors are using the quadratic formula. It's these numbers, and if you plug in k equals 3, that is 3 plus square root of 5 over 2, which is the square of the golden ratio. So that's the smallest stretch vector. In particular, I'll come back to this later, the algebraic degree of lambda can only be 2. So this is very interesting that the topology of the torus imposes this restriction on lambda, that it has to be very special. Its algebraic degree is allowed to be only 2. So the algebraic degree is the degree of the minimal polynomial of lambda. Now, so what about homogeneous surfaces? So for homogeneous surfaces, so we can look at the mapping class group of the surface, which is the homeomorphisms, orientation preserving homeomorphisms of the surface up to isotopy. Previously, we looked at the mapping class group of the torus. And so the Nielsen-Thurston classification says that there are 3 types of mapping classes. There are the finite ordered ones, for example, rotation of this surface by 1 click. There are these ones that are called pseudo-Anosov. So they are very much like the Anosov homomorphisms of the torus. They stretch in one direction by a factor and compress in the transverse direction by another factor. The difference is that here, these directions, these foliations have to have singularities. So maybe there are some singular points where there are maybe 3 leaves coming out of that singularity, or maybe even more than 3 leaves. And then the third type is reducible. So it's there are a bunch of curves on the surface, chopping up the surface into smaller portions, and these pieces might be permuted, but stabilizers are either finite order or pseudo-Anosov. So it's sort of a mixture of the previous 2. Now, the most interesting type is probably the pseudo-Anosov type. Also, most mapping classes are pseudo-Anosov in some sense. And also, these are the ones that have a number associated to them, the stretch vector. So these are the ones we will be interested in. Right, so we can ask again the same question. So what numbers can be pseudo-Anosov stretch vectors? Now, so it's known that a stretch vector lambda is always a bicaron algebraic unit. And so what does it mean? An algebraic unit is just a unit in the ring of algebraic integers, or in other words, it's a number whose minimal polynomial is monic and has constant coefficient plus or minus 1. And bicaron means that the Godel conjugates of lambda, except 1 over lambda, are all in this open annulus between lambda and 1 over lambda. So one of the big problems in the area of mapping class groups is Fried's problem: does every bicaron unit arise as a pseudo-Anosov stretch vector? Now, Fried originally asked this question with powers. So he asked whether every bicaron unit has some power that arises from as a pseudo-Anosov stretch vector, but eventually people thought that this is probably true without powers as well. Right. So this is still open, probably wide open, and not a lot of progress, but maybe. So maybe I like to say a few things about why this is difficult and some a little progress that happened recently. Right. So this is a realization problem, it's a construction problem. Someone gives us a number, right? And we need to construct a mapping class that has that stretch vector. So we need constructions for pseudonorms of mapping classes. And we have lots of constructions. We have Thurston's construction, fibrations of 3 manifolds. So one can construct pseudonorms of mapping classes by considering fibrations of 3 manifolds. One can construct new pseudonorms from old ones by branch coverings. There is cross construction, Hassan-Weiler's homological criterion, Panner's construction, Rosevich induction, train-check automata. There are many constructions. So why is this still difficult to answer this question? Well, so a construction would need to satisfy 2 crucial properties. One, it should be very general. It should be quite general to be able to construct maybe all pseudonorms of mapping classes, or at least like a big enough pool of pseudonorms of mapping classes. And the other thing that is just as important is that one able to specifically target a number with the construction. So if you have a desired number that you want to realize as thresh vector, then we need to be able to use a construction to try to tailor towards that number. And so two constructions that are pretty good in this second thing, being able to describe what the stretch vector is and target that number, is Thurston's construction and Panner's construction. There are several other constructions that are very general, and you can construct everything you want, but it's very difficult to try to control what number you get as a stretch vector. So let's look at these 2 constructions, Thurston's and Panner's. Now both use a similar framework, which is that we choose a set of filling curves. Filling means that the complement of the curves is a union of disks and once punctured disks. So it chops up the surface into very small pieces. And each construction uses products of Dane twists. So a Dane twist is an operation where you take a curve and you cut along the curve and you twist by a full twist and glue back. So we take a set of curves and we do Dane twists in a certain way, and if you do it in the right way, you get a pseudonorm of mapping class. So Thurston's construction, I'm not going to describe this in detail. I'm going to talk more about Panner's construction later. But so there's a bad news and a good news. The bad news is Thurston's construction is not general enough. So Huber and Landau proved in 2006 that if lambda is a stretch factor of a pseudonorm mapping class arising from Thurston's construction, then the trace field Q adjoin lambda plus 1 over lambda is totally real. So totally real means every Galois conjugate is real. So it's not lambda that has to be totally real. It's lambda plus 1 over lambda. Now, unfortunately, not every pseudonorm stretch factor has this property. So it's not good enough for constructing everything. But the good news is that recently Joshua Pankow constructed, proved that every Salem number has a power that arises as a pseudonorm stretch factor using Thurston's construction. And so a Salem number is an algebraic integer whose Galois conjugates, except one over lambda, lie exactly in the unit circle. So it's as bicurrent as it can possibly be. It's not. It's every other Galois conjugate is exactly in the middle on the unit circle. So this is very nice, but unfortunately, Salem numbers are very, very special. So here are all these categories in one picture. So Salem numbers is a is a pretty small subset of bipyramidal numbers. And for example, I drew piezo with a bigger circle than Salem because there is a theorem that saying that every Salem number can be approximated by piezo numbers. So, and also Salem numbers are conjectured to be, maybe even proven them, to be bounded away from 1, which is not at all true for bipyramidal units in general. So what about Penner's construction? So Penner's construction is a bit easier to describe. So we take two fielling multicurves. So a multicurve is just the union of disjoint curves. So the blue curves form a multicurve, and the red curves form a multicurve. And then the theorem says that every product of positive twists about AI and negative twists about Dj is going to be pseudo-Nosov as long as every twist is used at least once. For example, this product here is pseudo-Nosov. And then Penner conjectured in the same paper when he described the construction that every pseudo-Nosov mapping class has a power arising from Penner's construction. Now, if this was true, then it would be really nice because then this would tell us that we have a good chance of using Penner's construction to construct all bipyramidal units. But unfortunately, this is not true. With Hyunshik Shin, we proved that the Golomb conjugates of Penner stretch vectors, actually they cannot lie on the unit circle. So it's very interesting to me that like Thurston's construction and Penner's construction is so similar. But as you see in Thurston's construction, it seems that the easiest numbers to construct are the Salem numbers where all the Golomb conjugates are on the unit circle, and in Penner's, nothing can be on the unit circle, so it's like exactly the opposite end of the spectrum. And so the part 1 implies that the conjecture is false for most surfaces because there are pseudo-Nosov stretch vectors that have Golomb conjugates on the unit circle. All right. All right. So it's still an open question whether every bipyramidal unit with no Golomb conjugates on the unit circle arises from Penner's construction. So is this the only restriction, or are there more? So how we don't really understand how versatile is Penner's construction. Another question you can ask is, we know that Golomb conjugates cannot be on the unit circle, but can they at least be arbitrarily close to the unit circle, or where can they lie in the complex plane? So I showed that actually in this sense there are no more restrictions. So they can get arbitrarily close to the unit circle, they can be anywhere in the complex plane. And then going back to this degree question, we've seen that on the torus only degree 2 was possible. So we can ask if Penner's construction can be used to realize all possible algebraic degrees. So what do I mean by all possible? So on the torus, only degree 2 was possible, and Thurston showed that on the genus G surface, the degree has to be between 2 and 6G minus 6. And Long later showed that if the degree is odd, then it has to be at most 3g minus 3. So these are not very hard to prove constraints on the degree. And someone can wonder if all of these numbers, for given g, whether all of these numbers arise as stretch vectors. Back in 81, Arno Jokos gave a construction realizing the degree g. And then later, Shin gave a construction realizing degree 2g. These were not using Penner's construction. These constructions were by different methods, and very specifically tailored toward these degrees. I was able to show later that actually you can use Penner's construction to construct all of these degrees, satisfying these constraints. So in this sense, Penner's construction is pretty good. So here is a challenge that I attribute to Ian Nagel, because I've heard these ideas from him. So I think, I feel this is our best hope currently to solve this Fried's problem, realizing every bicaron unit as a pseudo-universal stretch vector. And so, so he suggested to use the ideas in Kenyon's paper, so embedding the Z lambda into RP as a lattice to realize a given lambda as a pseudo-universal stretch vector. So how should this work? So now, one fundamental difference is that in the Kenyon example, we had a plane and we had to tile a plane. So in that case, we looked at this two-dimensional subspace of this RD and tried to approximate it with a triangulation. Now in this case, we're looking at, we need to construct a surface, a compact surface. So, so one thing one can do is take a quotient of RD by this lattice to get a d-dimensional torus. And then multiplication by lambda induces a homomorphism of this d-dimensional torus. And so if you can construct a surface, a nice surface in this d-dimensional torus, so that's compact, so if you can construct a compact surface in that, and if this action, if this multiplication by lambda induces some sort of a nice homomorphism that embedded surface, then maybe we can get a surface homomorphism. Now one problem is that the surface cannot be embedded because the fundamental group of the d-dimensional torus is abelian, so and all these higher genus surfaces have non-abelian fundamental groups. So your surface would have to be emerged, possibly with branch points, so like it could be a branch surface. And there are other difficulties as well. So, but I think this is a really good idea, and really I thought a lot about this, and I couldn't make it work, but I think I'd be really interested in, really happy if this could be made work. Right, and yeah, in the last few minutes, I just want to give an idea of one of the theorems I mentioned earlier, one of the ideas for the proof. This theorem that the Galois conjugates of Penner stretch vectors lie off the unit circle. So how can you prove that the Galois conjugates are not on the unit circle? So one thing that's really nice about Penner's construction is that corresponding to these Dane twists in the construction, there are no matrices. So the product of the entries can be described by the product of the matrices, and the stretch factor of the product is just the largest eigenvalue of the product of matrices. So all you need to do is multiply matrices and compute the eigenvalue, and that's the stretch factor. So, so we need to show that these matrices that we get from this construction do not have eigenvalues on the unit circle. And now, an eigenvalue in the unit circle, by the real Jordan form, it's a rotation on an invariant plane. So we need to rule out rotations on invariant planes. And the way we do it is define a height on our space on which the matrix acts, so that every matrix, so every transformation increases the height. So if you keep multiplying these products, then after every iteration, the point we get to will have a bigger height. So if you had we clearly cannot have a rational rotation because we increase the height, and we should increase the height again, but it's not possible. But again, if this height function is continuous, then irrational rotations are also not possible because of continuity issues. So just one example for such height function. So these are two matrices that you can actually get from Penne's construction if you apply it on the torus. So these two shearing transformations. So one transformation shears vertically, one horizontally. And then here's a height function that works, xy. So it's this saddle-shaped function on the plane. And you can easily check that if you apply either of the two transformations, the height increases. For example, if you apply one of them, then x gets replaced by xy, right? So instead of this, you get xy times y, so it gets increased by y squared. Right. Yeah, that was the last thing I wanted to mention. Thank you very much.
Any questions for Balázs?
Do you get something more if instead of compact two manifolds, you allow those manifolds punctured at an invariant set?
So like finite many punctures on a compact manifold. There are still restrictions analogous to the compact case. So if you puncture more and more times, you can get higher and higher degrees, but there's still a finite bound given the surface. And in terms of what numbers arise as stretch factors, there's the same conjecture. So the same conjecture.
Are there any special cases where Hegel's idea works that you know of?
Yeah, so the easiest case should be the case where lambda does not have Galois conjugates on the unit circle, because as I mentioned, a Galois conjugate on the unit circle, that would mean like a rotation in the direction. So in that case, this map of the d-dimensional torus would not be an also. So if there's no eigenvalue on the unit circle, so if all the eigenvalues are strictly bigger than 1 in modulus or strictly smaller, then this homeomorphism of the torus is an also. So maybe you have some extra tools, maybe Markov partitions, or I don't know, something about the non-sorted homomorphisms. So that would be the easy case, but even that is I don't want to. Yeah.
Did you say anything about the product of eigenvalues often greater than 1 in modulus?
The product of eigenvalues.
The product of the lambda is larger than 1 in modulus.
Right, that's the Mahler measure, and people are
questions for Balázs? Let's thank him again. Semi-plenaries reconvene at 9:40.